Applications of Gauss's law. First one is conducting solid sphere or a spherical shell. Spherical shell, even if it is a dielectric or any material, it may not be a conductor, also no problem. So you try to understand this difference. For example, if the solid sphere is a conducting sphere, wherever you give charge, it doesn't matter, it goes to the surface. Surface only contains a charge. Surface charge density you have to calculate, that's it. Okay, if this solid sphere is made up of a dielectric, then charge resides even inside. That means solid dielectric spheres we are not doing here. Okay, whatever we are going to do derivation now, it is applicable for only conducting solid sphere, or else non-conducting spherical shell. Shell means inside cavity, hollow sphere. So charge resides only on the surface, but charge distribution should be uniform. This is very important. If it is made up of a solid conducting sphere, no doubt charge resides only on the outer surface uniformly. Okay. If it is a spherical shell, it made up of conductor or a dielectric or insulator, doesn't matter. Charge resides only on the outer surface because inside there is no matter. It is cavity, hollow. So charge resides only on the outer surface. But charge distribution must be uniform. This you have to understand. That is the meaning of spherical shell. Okay. If we take a sphere of radius r, Q amount of charge is distributed uniformly over the surface. I need to calculate electric field due to this sphere at a point outside the sphere. For example, I want to calculate here electric field. See, on which point you have to calculate electric field. You need to draw a Gaussian surface must passing through that point. We need to draw a Gaussian surface now. Why? Because we are applying Gauss law. So how to draw a Gaussian surface? See, Gaussian surface of any shape, doesn't matter, flux is same. But when you want to calculate electric field, usually if you can able to draw Gaussian surface in such a way that, I'll explain two conditions for that, then it is easy for you to calculate electric field. Okay, to calculate easily we are giving some sign conventions for Gaussian surface. First point we have to remember is, if you can able to draw a Gaussian surface in such a way that at any point on the Gaussian surface electric field is constant, magnitude should be constant. Magnitude at any point on the Gaussian surface is the same, then it is easy. So for this sphere, Gaussian surface will be again a sphere. You will get Gaussian surface as sphere. See, at any point on this Gaussian surface, magnitude of electric field is same because each and every point is equidistant from the center of the sphere. From this center, see, the entire charge is concentrated at one point, that is only called as a charge center. Okay, from charge center, every point is at equidistant. This is one important point. Second, for example, see, here positive charge is lying. So for positive charge, electric field will be radially outwards. So electric field will be radially outwards. So this is the direction of electric field. Electric field direction is radially outwards. Okay, if I want to calculate a electric field here I need to take a Gaussian elemental surface, say ds. ds bar, ds area vector is perpendicular to surface and outwards to the surface. That means ds bar is also in the direction of electric field. Angle between E bar and ds bar is 0 degree, or else angle between E bar and ds bar is 90 degrees. Okay, if we can able to draw Gaussian surface with these three conditions, one is electric field at any point on the surface magnitude should be same. Second one, the direction of electric field and area vector should be either parallel or perpendicular. Then it is easy to calculate electric field. So here for this sphere I have drawn Gaussian surface is sphere. So each and every point on the Gaussian surface is equidistant. So electric field I can imagine it is constant. So now one of the condition is satisfied here. Electric field and ds bar are in parallel. So I can calculate very easily here by the definition of Gauss's law. Circular integral of E bar dot ds bar is equal to charge enclosed divided by epsilon naught. I have imagined here charge q is distributed on this sphere. This sphere is maybe a conducting solid sphere or a spherical shell. Spherical shell may be conductor, may be insulator, or maybe dielectric, doesn't matter. Okay, so here you see circular integral of E bar dot ds bar can be written as E into ds into cos theta, because A bar dot B bar is AB cos theta. So similarly E into ds into cos theta is equal to charge enclosed divided by epsilon naught. Now see here theta is angle between E and ds. So from this here E and ds angle is 0 because they are parallel. So this is cos 0 degree. We know cos 0 is 1. So here moreover here you see electric field at any point on the Gaussian surface is constant. So I can write constant term outside the integration. So you will get E into integral of ds is equal to charge lying inside the Gaussian surface. Inside this surface I have entire charge. So I have written here q divided by epsilon naught. Okay, integral of ds is s. We know from our basics. Integral of dx is x, integral of dy is y, integral of ds is s. So s is surface area of Gaussian surface. This is important because I have taken ds is the elemental portion of the Gaussian surface. So that means this is Gaussian surface. See this particular point is at a distance small r. Here small r is greater than capital R. So E into S is equal to epsilon naught. I know surface area of a sphere is 4 pi r square. So E into 4 pi, which r I have to write, whether this capital R or small r. See where I am calculating electric field here. So I have to write the surface area of this Gaussian surface. So that's why it is small r. Small r square is equal to q by epsilon naught. Then I want to calculate only electric field. So E is equal to q divided by, I will write 4 pi epsilon naught together, 4 pi epsilon naught r square. So electric field E is equal to 1 by 4 pi epsilon naught q by r square. This is important. Here point is outside point where we have calculated electric field at any point outside the sphere. Okay, at any point outside sphere, that is small r is greater than capital R. So this is the electric field. Okay, similarly we will calculate electric field on the surface and at any point inside. Okay. See, for on the surface, I'll use the same thing, just you note down it as a separate. This you make it notes as at any point outside the sphere. Now I am going to do small modifications, then we'll get the answer that I am going to do now. See carefully. At any point on the surface means here just outside. Okay, I'll take Gaussian surface just outside. Okay, here this is the new Gaussian surface. At any point on the surface means it is just outside. At any point on the sphere that we are doing, see that point I have taken just outside. Just outside is also called as on the surface. See, this Gaussian surface radius is equal to capital R, because it is just outside, not for this much width. You imagine it is just outside. So small r is equal to capital R, on the surface or just outside distance. So integral of E bar dot ds bar is equal to charge enclosed by epsilon naught. You see here, if you take a point here, electric field and the elemental portion ds both are in the same direction. So angle is 0. So q by epsilon naught, E into ds into q by epsilon naught, E into s into q by epsilon naught. Here surface area is Gaussian surface as well as sphere surface is same, because I am saying point is on the surface. On the surface means small r is equal to capital R. So that's why I will write here capital R square. Then you will get here it is capital R square. Here it is capital R square. At any point on the sphere means small r is equal to capital R. So you will get E is equal to 1 by 4 pi epsilon naught q by capital R square. See, if the point is far, small r is greater than capital R, denominator is more, so electric field will be less at any point outside. If the point is approaching the sphere, distance decreases, that means electric field increases. So electric field increases as you move towards the sphere, it will be maximum on the surface. It will be maximum on the surface. This is a sphere of radius r. We need to calculate electric field at any point inside. That means I have to select a point inside which is at a distance small r from the center of the sphere. See here, in case of sphere, all the distances can be measured from center of the sphere. Okay, so I need to draw a Gaussian surface. So now see carefully here, to calculate electric field I need to use formula circular integral of E bar dot ds bar is equal to charge enclosed divided by epsilon naught. See, within this Gaussian surface no charge exists. Charge lies on the outer surface of the sphere. So within the Gaussian surface is charge 0. So that means here we should write 0 by epsilon naught, 0 by anything 0. So this is circular integral of E bar dot ds bar. Okay. So electric field becomes 0. Other than electric field in the left hand side, all will be sent that side. Okay. So 0 by anything 0. So electric field at any point inside is 0.